Hello and welcome to the 5th seminar about the Bethe Weizsäcker formula. On YouTube, the 4th seminar won't be uploaded because the 4th seminar was a seminar that I haven't held, but another member of the Discord server. And yes, I will only upload my parts here. Okay, a quick plan for today. We will do a quick refresh on the formula, how to use the formula, testing on different nuclides and some other calculations. And as a quick disclaimer, I have uploaded a separate video about the Bethe Weizsäcker formula, and I would highly recommend you watch this first and come back to this because all of the informations are based on the information that I gave in the video in a bit more detailed fashion. Okay, so this is what the formula looks like. It can be divided into 5 different parts. For example, we have the volume term, the surface term, the Coulomb term, the symmetry term, and the pairing term. And for all of these, you need constants. And if you look at the Karl-Heinrich Lisa, you will find these values for these constants. However, I would assume that most of you do not have this book available, but you will have Wikipedia. And in Wikipedia, you will see that these values deviate a bit more from this book. This is because the values are determined experimentally, and this is why we will have different values for each of these constants. For the sake of simplicity, I will use the Wikipedia values in order to do my calculations. I did the calculations in the video based on the ones from the Karl-Heinrich Lisa, and let's see where this will take us. Yeah, as a quick refresh, which I already did in the video, we have the iron 56 nucleus. So we have a nuclear number of 56, a proton number of 26, and a neutron number of 30, meaning that this is a GG nucleus. G coming from the German word gerade, meaning even, and sometimes there are also UG or UU nucleus. U coming from the German word ungerade, meaning uneven. Yeah, since 26 is an even number and 30 is also an even number, this is a GG nucleus, meaning that this last part will be positive or will stay positive. All right, if we plug in those numbers and plug in also these constants from the Wikipedia, yeah, we could calculate the binding energy per nucleon or the total binding energy, depending on what you do, for iron 56. If we just pay attention to the first part, so the volume term, we get 15.67 mega electron volts per nucleon. If we pay attention to some more, you might want to use this picture. This picture is quite handy if you want to check whether your calculations go into the right direction. Yeah. For iron, we are at the mass number of 56, so about here. And if we just look at the volume energy or volume term, we get a value that is above 14, so 15.67. Yeah, if we pay attention to the surface term, it corrects it down to 11.16. What I do with these different parts of the equation is explained in the detailed video, so I would just recommend you watch that. If we go further, we correct it down to then the actual value with all of these terms being paid attention, and this is 8.822 mega electron volts, and the literature says that the binding energy at the iron 56 nucleus is 8,790 kilo electron volts per nucleon, so 8.79 mega electron volts per nucleon. If we paid attention to the Karl-Heinrich Lisa, we would have this value, and they are quite close to each other. Okay. So I wanted to test this formula and see where this deviates from the literature. So I did this with the iron nucleus and I was off by 0.3%, which is really close. And I also did it for calcium-40. Why did I do it for calcium-40? Calcium-40 is a double magic nucleus, and since the Bethe Weizsäcker formula is based on the liquid drop model, which can't explain double magic nucleus, I expected the outcome to be quite different from the literature because, well, the double magic nuclides, they have a very high binding energy because of this effect of the double magic nuclides. And I was just off by 0.4% from the literature, which is higher than just for normal nuclides, but it's still within reason in my opinion. I also tested it on the very small scale, so for the deuterium atom, because it's the smallest one where we could even calculate mega electron volts per nucleon, because the hydrogen 1 is just 1 proton and you can't calculate that for just 1 proton, and we can see this is complete nonsense, so I would just not do it with very small atoms. On the other hand, I did it with very heavy elements for example Rutherfordium 261, and I was just off by 0.325%, which is really accurate. After running all of these calculations, I came up with the conclusion this Bethe-Weizsäcker formula will give surprisingly accurate values according to the literature when it comes to the binding energy per nucleon. And it's okay for double magic nuclides, since the liquid drop model doesn't explain it, but you will still get within reason. So 0.4% off is still quite good. And it only makes sense to apply this Bethe-Weizsäcker formula when you want to calculate the binding energy per nucleons if we look at nucleons at a proton number of above 20. So anything heavier than calcium. Otherwise, you will deviate from the literature by way too much. I also wanted to present you this formula. It exists by plugging in the nucleon number. You can determine the most stable proton number for a given isobar. In this case, we have the 32, and the proton number of 32 is germanium. And this is on the 73 isobar, the most stable nucleus. As we can see here, this is the only stable one. It's marked in black. And yeah, if we look at the Bethe-Weizsäcker formula yet again, we have two different isobars at the chart of nuclei. So we have a even and an uneven isobar. Yeah? The 73 is an uneven isobar, which means that the nuclear number is uneven, and this can either be achieved by having an even number of protons and an uneven number of neutrons, or vice versa. When we have an even number of protons and an uneven number of neutrons, or vice versa, we have a GU or a UG nucleus, meaning that this last part will be ignored. However, if we look at the even isobar, so for example the 74 or the 64 isobar, for example here the copper one, we can see that on this isobar, on the even isobar, we have two most stable nuclides. So if we decay from cobalt 64, which has a proton number of 27, meaning it has an uneven number of protons, in order to have an even number of nucleons, we also have to have an uneven number of neutrons. So we have a UU nucleus, and this will decay into a GG nucleus. So this means for the Bethe-Weizsäcker formula that this part will change from negative to positive. And we hop between those parabolas all of the time until we go to the, in this case, the zinc one. Came from here down to the zinc one. This zinc has a proton number of 30, meaning that this is a GG nucleus. This part is positive. If we were to theoretically decay down, we will change the GG nucleus to a UU nucleus, meaning that this part would become negative, decreasing our binding energy per nucleon, meaning that this copper 64 isotope would be less stable than the zinc 64 atom, which means that the zinc won't decay up to the copper. Yep. Okay, coming back to the topic, I just wanted to mention that the Bethe-Weizsäcker formula can explain why we have two stable nuclei on a given isobar if this isobar is a even isobar, because we have a plus sign and a minus sign. So we have a UU nucleus which has a minus sign and two GG nucleus that are quite near this valley here that have a positive sign on this last part in order for them to be more stable than one between both of them. I also wanted to mention the fission parameter because the liquid drop model and the Bethe-Weizsäcker formula are exceptionally well designed for explaining nuclear fission. And yes, when doing nuclear fission, the nucleus is deformed quite drastically. And in this deformation, the volume term will stay the same because, well, if you squish a ball, the volume will stay the same. And the asymmetry term and the delta will also stay the same because, well, the neutron axis don't change if the form of the nucleus changes. Therefore, you won't make a change in the neutron number, and therefore you won't make a change if it's a GG or GU nucleus, and so on and so on. But what will change is the Coulomb term, which gets smaller because the charges that will repel each other are separated a bit further because of this deformation, and also you have the surface term which increases because of this deformation. You can look at this formula, which already has thrown out all of the different terms that don't change, and you can determine a fission parameter. For iron, you have a fission parameter of 0.205. What does that mean? Well, a fission parameter of x being less than 1 means that it's stable against small deformation. X equal 1 means that spontaneous fission is expected as the only type of decay. Well, I tried it for organesson and I got an x value of 0.8, which means that organesson also does decays other than spontaneous fission, for example alpha, which is true, to be honest. So if there was to be an element that has a fission parameter of x equal 1, you would expect it to only do spontaneous fission. I just wanted to get that out. With that being said, thank you for your attention and goodbye.